Okay, so hello, name is Justin, and this is my first YouTube video. So, like the title says, we would be looking deeply into Doubly linked lists. So, a bit about me and um, a student. So, the way I practically try and explain this is that I try to do the work myself, and as I'm doing the work myself, there's also a possibility that I can also run into mistakes as well because I'm not also good at this stuff as well. And since that's the case, um, mm, um, I would also have to consult the internet too. So yeah, I'm also a beginner, I'm also a student. I'm not really an expert in all this kind of stuff. This is more like a follow me as I teach you slash learn how to do this stuff myself. And I'm actually a student from the University of New Brunswick here in Canada. So yeah, I'm a student of that university studying computer science. And I'm actually in my final year, fourth year. So starting from um, D4. So yeah, so I'm going to give you guys a rundown of what I am doing. So basically, if you can see on my screen, we are doing basically a list of functions that we have to implement using a doubly linked list. So the first thing that we're looking at is the basically the definition of the doubly linked list. So the doubly linked list is basically this is also how I understand it. A box and we have a pointer that points that box to another box and we have a pointer that points it to the previous box. So we basically have two pointers, and if you look at the highlighted text that I just highlighted, you would see that in this definition we have type-def struct node. Type-def is basically a way of renaming the structure to node so that every time that we try to call the structure, we don't have to basically write struct node every time, right? We just name it node so that it kind of just saves you time as you're declaring it everywhere you use it in all the functions that you implement. And we also have this. This is a node pointer. So a node pointer that is attached to the general node that points to a previous node. So like you have a box, just points. So this points to a box that came before it, and the stroke node next is another box. So like the next is pointing to the next box, the previous is pointing to the previous box. So they're like um, pointers in C. Oh, and if I didn't make that clear, we are actually writing this linked list functions in C. This is a C program. So that's where all these pointers come from because C is very, very close to the hardware. So we get to see memory and how memory allocation works. Oh yeah, I forgot. So that's a char pointer because in C strings don't exist. We don't have string types like Java or Python. So basically, um, let's say you had a word called hello, and the thing is that basically a char pointer basically points to the first char in memory, and then it basically keeps going until you find the terminator. You know, it's called, yeah, it's just like a way of ending the string so that like when char keeps going and it sees this, it knows that that's the end and this is just everything that it theoretically pointing to. But just note that the char pointer actually points to the first char, and then it knows that the next memory location are the rest of the chars till it reaches the terminator. So that's that. Um, so the first function that we implemented was void add, and how void add works is that it takes in a basically a value like a char value, um, which is indirectly a string. So okay, so here's my rule of thumbs. Anytime you see this, just assume it's a string. Even if strings don't exist in C, this is basically just what a string looks like in C. And what this is a pointer to the first node in a linked list, but then it's a special kind of pointer. It's kind of a pointer to a pointer. Let me explain. So in a linked list, to start a linked list, you need a head, and the head is hello, and this is the previous, and this is the next. And basically, the next and the previous are currently pointing to no because we don't have any other nodes in this linked list. So what's actually happening is that we need to also note that head itself is a pointer. So and the reason why we're passing a pointer to a pointer is because when you enter a function in C, you basically duplicate this because the thing is that you don't actually pass the same pointer into a function. In fact, anything that you pass inside a function is a duplicate of whatever you're trying to pass in. So you basically get a copy of the head that points to hello. And this isn't usually a problem in C because at the end of the day, the copies are pointing to the same value that you want to change. So if you wanted to change anything, it's still going to work, even if it's a duplicate. The only thing that's going to happen is that when the function is over, like when you're done with the function, the copy gets deleted. But whatever you already modified stays the same. That's why pointers are very important in C. But the issue is that if we wanted to add a value to the function, the thing is that since this is a copy of head, whatever we add using this, because let's say that we want there was no node in the whole linked list, like the linked list was empty and we created a new node and made it the head. If we do that and then we end the function, that head is going to get deleted plus the new node that we already created. And this head, the original head, has no knowledge that this head made anything because they're different. And if that happens, then head would always point to no, and you've basically not done anything. So it's only the situation where it involves head that node star star exists. So now that we know that, we can use that knowledge and create node star star. So what node star star does it is that it references the original head itself and does not create a copy of head like using normal node does. And what that basically does is that it basically references head itself and it's like assume that head is in address 600, right? So node star star head is basically going to look for the address where the original head is, and then it's going to reference the address. But then here's the problem with this. Head itself isn't really useful because that's just where the pointer exists in memory. We're not actually getting what it's pointing to, which is the allocation of the node that are going to create later. It's just pointing to head. So if you use star head, because this star is a dereferencer, so it basically um, says, okay, so we've seen the address of where head is, which is like address 600, and then we're going to dereference that head to see where that points to. And let's assume that we are going to create a new node in address 700. Star head points to 700 where that new node is going to be created, and then that's how you work with node star star, because we're basically now pointing to the address of the original head, then pointing to where the address of that head is pointing to, so that when we create a new node, it basically remembers that it's the original head that we're referencing in this whole function. And so if you look at this line, what's basically happening here is that we're basically allocating memory for a new node that we're going to create, and we are going to make new node points to it. So basically, it's like malloc creates a new space in memory, and with this new space in memory, new node points to that space so that whatever that we want to create as a new node, which is like the next pointer, the previous pointer, and the data string, it would all fit into this newly allocated memory that we created, which is very different from other programming languages because other programming languages basically create the memory without you explicitly asking for it. So you always know that there's a memory there. But like in C, you basically create it and then you also have to free it by yourself. So it's C is more hands-on than Java or Python. And so what you now do is that now that you created this new space, you basically have a previous pointer. But since previous isn't pointing to anything for a new node, we set it to no. So that's no. And the new node data would be basically what we do for this is that we want to create a new memory allocation for where we're going to store um, whatever new node data is pointing to. The reason why we want to do that is because if we just made new node data point to um, value, anytime that we modify it, we're basically modifying the same points in memory. Okay, so like let's say that we had hello. This is basically the original memory allocated space that was given to value. So if new node um, data is equals to hello, then anything can also be pointing to this. Like if we had um, current data, and then if current data modifies hello to high, then let's say we run that function again, we would have been expecting it to still be hello, but then it's going to be high because everything, every single thing that you call that points to this area changes that irreversibly. So you lose the original data that was inside. That's why anytime that we create a new node, we basically create a new memory allocation and copy the value of that string into it so that every single new node has its own allocated space for the value. So we create that that's what this um, three lines are, sorry, these two lines are for. New node data is equals to memory allocation. We basically get the length of the string and we add the string terminator as well. That's what the plus one is for. And then we basically copy the value itself into what new node data is pointing to so that we now have a copy of wherever value is in here. And new node next is no. Okay, so this line is basically saying if head is equals to no, then we make head equals to the new node. So because if you were to add a new node and the linked list is empty, its head is obviously going to be no because there's nothing. So then you just add the new node and make that equals to head. And this is where, let's say we had a node already inside the linked list. Like if we had, so what this does is that we give this a pointer. So current basically points to head. And then what current is that current is a subsidiary to, it's like a middleman to node. So current is basically in charge of modifying or making any changes to the linked list itself. So current is currently pointing to head, and if the next thing that current is pointing to is no, then we don't enter the while loop. We know that that is no, so we give that a new node. We give that a new node, and that's basically how it works. But then, if you remember, if you remember, when you give current new node, sorry, current dot next new node, you also need to remember about previous too, because in doubly linked list, which is the difference in single linked list, because if we had single linked list, all we had to do was just point forward. But we also want the new node to point back to the first node, which is head. So in order to do that, you have to make new node previous point back to current, because current is still in the first node. It's just current dot next that is equals to the new node. So that's that. That's how to add. So we now go to void delete. So we also pass in the address of the original head and also the address of the pointer that points to the value. And if you look at the first if statement, if head is equals to no, then we basically um, exit the whole program, because it prevents errors, because you can't delete a node that doesn't exist. So this just exits the whole program. And if you are deleting head itself, you use this. This is string compare. It compares the original head to see if the value of what you're trying to delete is the same. So basically the data of the original head and the value that was given, if it's the same, then firstly you check to see if head the head next is equals to no. The reason why we're doing this is because if the head next is no and we accidentally reference it, it's going to cause an error or crash the program, because in C you can't dereference a null pointer. It's kind of forbidden. So that's why we have that if statement to prevent something like that from happening. And this is the case of if it was only head that was inside that function. If we had other nodes, then this if statement is always going to fail. So, sorry, not other function, other nodes, my bad. Um, so we free head and then we return. So freeing is basically you telling the memory allocation that we're done with whatever space you've given us, you can have it back. So we free it and return it. So save as is basically a situation where we had one more than one node apart from the head. So if we had something like two nodes, for instance, save as is going to represent the next node, and then we try to make save as previous equals to null because we're getting rid of the head. So the next node is going to not point to anything back. And then we free head, and then we make head the next node. So this else is if we're not actually deleting the head, we're deleting something else in the linked list, like another new node. So we make current points to the next node apart from the head, and we make previous points to head. So what we're going to do is that we basically go into the while loop and say current should not be equals to null because we want current to traverse throughout the linked list until it reaches null. That's when the while function ends. Then we check and see that if current.next is equals to null. So basically what this is saying is that current.next is equals to null, then that means current should probably be at the last new node in the linked list. So basically this specific if statement is for an instance where we have something like this. So current is basically resting on this new node, and then the next thing is null. The reason for this is because if we try to um, reference the next node, it's going to cause an error. So we're trying to catch that by using this if before that happens, and then we free it in a special way. What we do is that we now check that specific new node to see if it's the same as the value. If it's the same, what we do is that we basically take previous because previous is going to be here at this point, and I'll show you why. So previous is going to be here at this point, and we're basically going to be like previous dot next is going to be null. So it's basically going to cut this off and make the next pointer null, and then we free current. So it's basically only going to be this left because we've deleted the last node. So this is going to be the remaining new node in the linked list, and we return. Return means that you just exit the function itself. But like if this is not the case and it's just a random new node, it's very easy. All you have to do is just check to see if it's the same thing. If it is, then previous.next, I'm actually going to draw this out. Okay, so previous dot next, it's basically called previous arrow next, but I'm using dots because I feel like that's easier to say. But like, just to note, they're not the same thing. And if you actually write dots, C is going to give you an arrow because that's not really how you write that in C. It's arrow. So previous dot next is basically going to be equals to current dot next. So current dot next actually points to value. Previous dot next points to current. So we're just overwriting it with current dot next. So previous dot next will now point here. The reason why we're doing that is quite simple. Look at the next line. So previous dot next is going to be previous dot next dot previous. We're basically calling this, and we're going to make it point to previous. So now what we've done is that we basically isolated current because now nothing is equals to current anymore. So we now free current and um, we return. And then there is absolutely nothing that um, current is going to do because current is gone. So it's just this. So this is what happens if we try to delete in between new nodes in the linked list. We basically eliminate this, and then we have yeah, we've basically done deletion for that. And I know that you've probably been wondering, okay, so how does previous and current actually teleport? Like, how do they move? So that's what these two lines are for. So previous is going to be equals to current. Then current is now going to be equals to current dot next. So current basically overwrites itself to move forward. So that's how delete works. And we have count items and remove duplicates. So count items, how count items work is very simple. How it works is this. All we want to do is that we want to look for um, an amount of new nodes that have the same value. So basically all we need for that is a counter. So we initialize the counter and we make it equals to 0. And then we check to see if there's even any new nodes in the linked list at all. If the linked list is empty, head is going to be equals to null and we exit the program itself. But if that's not the case, we set currents to be head and then we use currents to look through the linked list. And then we check and we're like, okay, if current data and value the same, then just increment counter because we found a new node that actually has what we're looking for. And then you keep traversing through by using current equals to current dot next. So you just keep traversing through, you keep comparing, and then if you finish the linked list, then you can now return how many you found. That's all count item does. Okay, so we now have another one. So as of now, I haven't actually finished implementing this, but in the next video, I will try to write this down from scratch because we still have other functions to implement. So I'm going to try and implement remove duplicates from scratch and we would go from So yeah, okay. So quietly trying to see if I can make this YouTube stuff work and also learn at the same time. So thank you for watching and see you in the next one.